Want to continue with our classes, mathematics, and implementing the same in Rust. So we had looked at prime numbers, how to write the code for prime numbers and how to factorize a composite number using Rust. So today I want us to look at Euclidean algorithm, then the extended Euclidean algorithm, and how to implement them in Rust. But before that, we have to see how we do it manually, just one or two examples on how to do it manually, and then how to do it in Rust. Of course, when you understand how it's done manually, you can now understand how to write the code, the Rust code. Now, so Euclidean algorithm, we just, it's not an algorithm as such, but we use it to compute GCD of numbers by factoring factoring the number. So of course we are using long division and doing it severally, successive times. So if you have two numbers, you take the smaller number and you divide into the bigger one until the remainder is 0. So that is how we calculate GCD, and we shall see how that is done. The definition of the division algorithm, before we look at a Euclidean algorithm, because we normally use division algorithm in the Euclidean algorithm. Division algorithm, if you have two numbers, A and B, we're just asking ourselves, if B were to go into A, how many times will it go there? And what will be the remainder? That's what I mean by division algorithm. So for instance, this equation says that if we have two numbers A and B, then A, B can go into A Q times, and the remainder will be R. Of course, R should be smaller than the divisor and should be bigger than 0 or equal to 0. That's the division algorithm. For instance, if I'm given that 4 and 5, then we can say that 5 goes into that 4 6 times, and the remainder is 4. So this is what we call division algorithm. Now, what about Euclidean algorithm? So Euclidean algorithm, what we are doing, that division, we are continuing the division until we get the remainder becomes 0. So you can see in this case, our remainder is 4. So that means for us to do division Euclidean algorithm, this 4 again now becomes a divisor in the next step. The 4 becomes a divisor, and we ask ourselves how many times would the 4 go into 5, and so on, until the remainder is 0. So I want to take an example. We have these two numbers, 60 and 36, and we want to use the Euclidean algorithm to find the GCD. Of course, we said Euclidean algorithm is used to find the GCD of two numbers. So for us to do that, we apply division algorithm in each step. So first, the two numbers, 36 and 60, 36 goes here once, and the remainder is 24. So we're going until this remainder becomes 0. So we ask ourselves, in the next step, again, we use the division algorithm, ask ourselves that 24 into 36, how many times? So 24 go there once, and the remainder will be 12. And then what about 12 into 24? To go there twice, and the remainder is 0. So we've achieved the remainder of 0. So that means the GCD is the remainder just above this remainder of 0. So the remainder just above there is 12. That means the GCD of these two numbers, therefore, is 12. So that is what, if you write a code, that is how the code is supposed to work. The code is supposed to be finding remainders, and until the remainder of 0. Then it's supposed to understand that this remainder then becomes the GCD, the one just above this 0. Now, so I've just said here that to compute GCD of two numbers by Euclidean algorithm is just to find the GCD by repeated long division, as you note the remainder at every stage. Just one more example, then again we look what the code. We have these two numbers. So we want the GCD. We ask ourselves 715 to that, the 16, and this will be the remainder. And then this remainder goes here once. The remainder goes here once, and the new remainder now is 252. That is the new remainder. Now this new remainder now becomes a number. We can call it B. When you're writing our code. Now B goes into A, the new A. So you can see at every point, if we began with A and B, and they're changing. So we say the mutable. A is mutable and B is mutable. That means they're not fixed, they're changing at every stage. This was our A to begin with, and this was our B, and the remainder is there, our remainder. So then B goes into A 16 times, that is the remainder. Then the next time, this remainder now becomes B. This remainder now becomes B. And our B becomes A. What was B now becomes A. What was B becomes A. So that means, yes. So now this B goes into this A once, and the remainder is this. This remainder now becomes our next B. He said B is mutable. So it's changing. Now, so the new B now is that 252. And now our new A was now what was previously B becomes our A, which is 504. Then we ask ourselves, B into A, how many times? And the remainder is 0. So now this, what has been our B? What has been our B becomes our GCD. What has been our B becomes our GCD. So that's how we write our code. And let me just show you the code now, because the code we have to get to know that the two numbers are changing. We began with A and B, but they're changing and therefore they're mutable. So when you're writing the code, that has to be at the back of our mind so that we are able to do it. I'll not show this example. You look at it later. Just go to the code. Now, the code is this short. This is our function. So we define our numbers. And let me call this our A, our number 1, and then our number 2. Of course, we are dealing with the two numbers. And then this one is to call the Euclidean algorithm function. So it calls the Euclidean algorithm function with the two numbers, number 1 and number 2, which of course have been, let me invite this, which of course have been defined above. So we begin by defining those two numbers. Now, so this is a function, the main function. You've defined your first number, you've defined the second number, and then this to call the Euclidean algorithm function that has the two numbers, number 1 and number 2. And then it has to calculate the GCD, and after that, it then prints the result. And you can see the result, the GCD of the first number A and B is, and you can see that one has been put here, is that this first bracket for the first number, and these are the brackets of the second number. And then the third bracket is the GCD. Now, this is now where the calculation happens. This is where the calculation happens. This function, we have the mutable A. This is our number A. It's an I64 number. You remember I said that when you want to deal with the negative numbers and positive numbers together, then you will use I. 64 means 64 bits. 64 bits is just 2 raised to 64 minus 1. That's what it means. So it will be in this range. It will be in that range. But now, since it's I64, it means a half of this will be positive numbers, and a half of this will be negative numbers. So that means that is the range within which you can ask for the GCD of those. So that means, see, for this one is I64. So this number can be handled. We can handle up to 4 million, and something positive numbers, and 4 million negative numbers. But beyond that, it will not handle, because we've defined it to be I64. You can also define I32, but that means you're now dealing with very few numbers. I16, very few numbers, and so on. I8, very few numbers. Now, but if you use U64, we said then you are only dealing with only positive numbers. But in this case, we're interested with the negative numbers. We know that the GCD of two numbers can be negative, can also be positive. And we also know that we can find GCD of negative numbers. And so since we are interested with both the negative and positive numbers, we then use I. So A and B defined, then they'll give rise to an I64 integer. They'll give rise to an I64 integer also. That means it can be positive or negative, and is 64 bits. Now, so then we enter this loop. We enter the loop. What does the loop say? You had two numbers A and B. So the loop says that while B is not equal to 0, while B is 0. Now you see, this one is B is equals to 0. So what that means, this loop, it means is the loop will continue. The loop will continue. What is happening in this, what is happening here would continue happening until B is 0. Whatever is here, that is what this means. Whatever is happening here would continue happening until B is 0. That's what this while means. So what is inside? What is happening here? Let's look at what is happening. What is happening is that B is stored temporarily. So it's just, this is, you let B be temporal. So for instance, this is our B120. So we let it be, we let B temp. So that means it's temporal. It's temporal. So 121. We let, just a minute, let me just write it properly. $121. And then, so it's this one is just temporal. So this B here that we're beginning with is temporal. We've said this thing is mutable, so it's changing. So that's why temp is used. Now, so we let it be temporal, and then the real B becomes, this means the remainder of A on division by B, the temporal number here. So now B is A, the remainder of A on division by B. So in this case, what am I seeing? What am I seeing here? What I'm seeing, I have A as 758. And then the temporal B is 121. So what is now B? What is now B? So this number is just put there temporarily. B becomes the remainder on division of A by B. This is what that's what it means. So what is the remainder on division? Let me just use my calculator. Oh, you've already seen the code, so I'm just explaining how the code would then be working. So I have 758 divided by 121, goes there 6 times, and the remainder is 32. So B is 32. What about A? A is what was temporary here. What was temporary? So what was this? What this statement means? That A now becomes what was here. So A is now 121. So we do it, and look at this. We do it until B is 0. We do it until B is 0. So while B is not 0, we just continue the process. We continue that process. So B is not 0. B is 32. So it means we continue the process. So what does the process say? B becomes temporary. So now our temp is 32. Our temp is 32. Let temp that be 32. What is B? B is A, the remainder of A on division by B. So what is that? This is our A and this is our B. So 121 on division by 32 was the 3 times, and the remainder is 25. I don't know whether I've done it properly. The remainder is 25. So this is our B. What about A? A is what was, this is where it's written. A equals to the temporary number that was there. The temporary number that we had was 32. So this is how this function is working. Then again, our B is not 0, so the loop says we continue. So that means let our temp this time be 25. What about B? B is the remainder. When you take that changing, A is changing, they are mutable. B is also a changing, is mutable. So B on division by A on division by B, the remainder is 7. What about A? A is the number which was temporal. It's 25. B is not 0. So again, we proceed. We proceed and say let temp be the B which is now 7. What is B? B is the remainder of A, which is 25, On division by 7, and that remainder is 4. And A becomes the number which was temporary. And so on. So this process continues until we have a B which is 0. So you can see at this point, we would now say let temp be 4. Is it 4? Yes, 4. Yes, 4 is B. And we will then say B now becomes this divided by that. The remainder is 1. The remainder is 1 because it was there. Is it 1? 4 into that. No, it will be 4 into 25. How many times? No, it will be the remainder will be what? 4 divided by 25, 40, no, 25 divided by 4, what do you get? It will go there 6 times. And the remainder is 1, of course. The remainder is 1. Go there 6 times, the remainder is 1. And what about A? A becomes 4. So then the last step, this is now the last step. We let our temp be 4. No, 1. It's B, 1. So that our A, our B, now 4 on division by that, the remainder is 0. What about A? A is what was temporary. What was temporary is 4. Now, what does this say? Our A here becomes the GCD. This is what it says, our A becomes the GCD. So the A that you left with becomes the GCD. So I don't know whether my working was correct. I think the working was, I may have missed somewhere because the GCD of these two numbers cannot be 4. I may have missed somewhere in my division and noting the remainders. But of course, that is how this algorithm works. I'll show you an example. So I've just explained what the first bit means. This first bit I've explained here. This one is supposed to be this. I've said that this function defines a function that takes 2 mutable I64 integers, A and B, and returns an I64 integer. The while loop, I also said that it runs as long as B is not 0. So as long as B is not 0, it will, whatever is happening inside that loop will continue happening. Now I've said that whatever is happening, the first iteration, second, and each iteration, the value of B is stored in a temporary variable temp. So the value of B is stored temporarily. B is then updated to the remainder of A divided by B. The remainder of A divided by B, that now becomes our new B. And A is updated to be the number that was temporary. So the number that was temporary is now our A. This is what this part means. So you need to know all this, what they mean, so that you can easily write the code without necessarily having to memorize the codes. Now, I've just looked at this example just to explain that. I'm looking at, yeah, these are the two numbers that, are they the ones that I have here? Now the ones that I have here were 758 and that. So I used different ones. I have the first number and the second number. So initially, this is my A and this is my B. And then the temp is the value of B. You make it temporary. And then what is this? It's supposed to be A. No, what I've written here. No. It's supposed to be, this one is supposed to be here. Supposed to be here. B is A, the remainder of A on division by 756. And this remainder is 504. This remainder is 504. And then A becomes the value which was temporary. That is the first step. In the second step, now we know what B is. It's made temporary. And now what does our B become? Our B becomes the remainder of A on the remainder when you divide A by B. But what is A? Our A is this now, 756. Oh, I've written it here. It went to another step. So I've written it. It's there. It's because the space, I think the space was small. So B is this, the remainder of this on division by that. And this remainder is 252. So this is our B. So this is just the same statement. It's just broken, but it's the same statement supposed to be. B is the remainder on dividing 756 by 504. That remainder is this. Now, so what is A now? Our A is what was temporary. We got the third step, the third iteration. The temporary value is our B, which is 252. What about B? B is the remainder on dividing A by B. This is our A, and this is our B. So when you divide, the remainder is 0. What is A? A is the value which was temporary. Once B is 0, as it is here, the case here, the loop exits. And when the loop exits, according to the definition here, it gives us 3 values. It gives us the GCD of this number, and this number is this number. And the number that it's reading is here. It's reading this number here. That is what we have seen. That's what we have seen in our example. We've reached here. So the loop exits and returns 252 as the GCD of these two numbers. Now, so that's how this function would then work. That's how this that's how this code will then function. Unless somebody has a question or something to chip in. Okay. Now, so I've showed another example here, but this one I've not. Oh, so let me just now run the code and we see if how the code runs. I think that I was almost forgetting to show you how it runs. Just open it. Just a minute. Let me first of all open it. Okay, are you able to see my code?
Yes.
Can you hear me?
Yes.
You can see what I've shared, eh? The
Yes.
code.
Yes. It's on
What
screen.
are you saying?
Your code on VS Code.
Can you see the numbers inside the numbers that number 1 and number 2?
Yes. 161 and 713.
Yes, thank you. Let's run this and see if it gives us the GCD. The result is here. Says the GCD of 161 and 713 is 23. Okay. Let's increase the number a bit. Because we are dealing with the I-64, so we can still increase the number. And I'm just writing here. I don't know what I've written. I've just added the numbers. Let's find out if it will do that. It has given us the GCD as 1. So it means that these two numbers are relatively prime. These two numbers are relatively prime. But of course, you saw how that it took a bit some time as compared to the earlier one, because the steps that are occurring here are many. The iterations, those iterations are more for this question than for the previous one, because the numbers are bigger. So the first A, the first B, and so on, then they change to the next A and next B, and so on. Those steps are more. So we expect that when there are more, it takes more time. And of course, if there are very big numbers that have so many steps, then of course it can take longer than this one. That's how this Euclidean algorithm works to give us GCD. It's a very simple code and very short as this. Okay, so the next thing I want us to look at is the relationship between LCM and GCD. And I begin that by showing an example. The example is find the GCD and the LCM of these two numbers, then compare. I want the relationship, if there is the relationship between LCM, GCD, and the product of these two numbers. Now, when you do that, when you factor this number, you find that it can be written as a product of its prime factors this way, and this other one as a product of its prime factors that way. So the GCD are those values which are common. For instance, I can see 2 is common, and of course it's the only one. 2 is the only one which is common. That means the GCD is 2. What about the LCM? The LCM, you shall pick anything that exists here. And if they are common, we take one which has a higher power. For instance, 2 exists and 2 has only power 1, so we pick it. I can see 3 here, but it's not there. It's not in the 98. But since it exists here, we pick it. And then there's a 5 which exists here as a prime factor of 270. Although it's not a prime factor of 98, we pick it. And then I can see 7 raised to 2 as a factor here, or 98, but it's not a factor of 270, but we again pick it. And so that gives us our LCM to be, this is our LCM. Now, so what is the relationship? You can see that if the product of these 2 numbers is this, the product of the 2 numbers that were given to us is that, and the GCD is 2. So if I take this product divided by 2, I can arrive at the LCM. So in other words, what we are then saying is that the LCM of 2 numbers, can be obtained by the product of those 2 numbers. Let me say that the 2 numbers are N and M. So the product of these 2 numbers, of course, you make it, you take the absolute values. That means you're only taking the positive. So if the product is negative, then you drop the negative sign. You only take the positive part. That's why I put it inside these parallel lines. Those are absolute values. So we're only interested with the positive values. And then divided by the GCD, of N and M. So this is the relationship. So we want to write a code. So the code to do this again would do the same thing. This code, for it to get the LCM, first it must get the GCD, then it must get the product of the 2 numbers, then it must get the quotient. The product divided by the GCD, that gives us the LCM. So if you want to write the LCM, the code to give the LCM, then that code, for you to write it, you must know this relationship. I don't think there's any other shortcut that you can write to find the LCM of 2 numbers. So for you to write the LCM, a code that will give you the LCM of 2 numbers, this relationship must be known. You must know that for you to get the LCM, you need the product of the 2 numbers. And then you need the GCD. Of course, GCD, we're just using the code that is above. The Euclidean algorithm. The Euclidean algorithm. So the Euclidean algorithm will give us, with this part we know. This other part we also know how to write the product of 2 numbers. Then we just tell the program that you divide the GCD into that. What you come up with is then the LCM. So this is, it is here. This is our code. And we wrote it because we understood the relationship. So you can see again, the first bit, we're just giving the first number and then the second number. Then we are saying, let the LCM result. So it's calling this function to give us the result of the LCM of the 2 numbers. So the function will give us the LCM of 2 numbers, M1, number 1 and number 2. And then it will print the LCM of this number, and this number is this. And that's why you can see these 3 things here. First number. So the first number is, this is the bracket for the first number. And this is the bracket for the second number. And then this is the bracket for the LCM. Now, so then we've already said for us to do this, we need to know first of all, we must find the GCD, and this one you already have it. You already have it from above. You already have it, so you just put it here. Just put it here. Just the same thing. So this part is to give us the GCD. So this part gives us the GCD. GCD. And now there's this function now here. Function give us the LCM of a number which is this is positive, U64, U64, and U64. B is also U64, and the result is also a U64. And what does it say here? It says that this LCM will be the product of these two numbers divided by the GCD. This is what it says here. So for us to do that, I said already that we need to know the relationship between the LCM and the GCD. Otherwise, we cannot do that. Okay, there's no other shortcut, I believe. There's no shortcut for writing LCM direct. Oh, I needed to show, do I have that? Let me see if I have it. Okay, let me just open. Just share that. Can you see what I'm sharing also?
Yes.
Yes, this is the code for obtain the LCM. We've already said this first bit, you have it. We just telling the function that we want the GCD. And of course, our GCD will be this A. And I've shown you the steps how we arrive at that A. That becomes our GCD. And then we are telling another function here. We are telling it that the LCM of this number A and number B would be a number here, which is given by the product of A and B divided by the GCD of A and B. Let's find out if it gives us the LCM. It is telling us that the LCM of these two numbers, this is why it has written the result, is 13 to 30. Okay, let's try a smaller number that we know. We know the LCM of 3 and 4. Let us see if it can give us. I think the LCM is supposed to be 12 for what? Saying that the LCM of 4 and 3 is 12. Let's try a bigger number. Let's see if if it can do that. Saying that the LCM of those two numbers is this. Of course, this is possible because this number is still within the range U64, still within that range. But if it goes beyond that range, then U64 will not be able to handle it. Let's try and move closer. Let's try and move closer and see. I don't know whether we've reached there. This one is still small. You can see it's here. So it's telling us the LCM. It's telling us the LCM of those two numbers is this. It's a bigger number, slightly bigger. Yes, this number is about 16 what? No, this is a bigger number. So let's again increase a bit. Let's increase and see what we get. If it will give us a result. Yeah, so you can see there's some panic. There's some panic here. And what does it say? The thread panicked because the attempt to multiply with overflow. Overflow means it went beyond what U64 can handle. It went beyond what 64 can handle. Let's see. What about if we change this? If we change this to 128, let's just change and see what we get, if it can give us some result. Let's just change this. Let's see if, to change this part also. Just trying and to see whether to give us something, because there was an overflow when we tried to use U64. Now this one has worked. So you can see the number that we get. Of course, this number is beyond what U64 can handle. So for you to handle bigger numbers, you just change. You use 164 to 128. You can change even to a bigger number. That means the bits, just 2 raised to that number minus 1, the bits. You can see this is a slightly bigger number. It's a slightly bigger number. Oh, there's an overflow. It has given us some result here. It's a bigger number also, a very big, but of course, this is how it works. This is how the LCM code, Rust code will then work to give us the LCM. Good, so there's an assignment here. The assignment says use Euclidean algorithm to compute the following GCDs. So you can do that. You write the code and try to do that. And then also write the code for the LCM and do the following questions. Of course, the questions continue up to here. So you're using the Rust code. You've seen once you know to write the one for the Euclidean algorithm, then the one for the LCM becomes very easy. Now let's look at the extended Euclidean algorithm. Now, the Euclidean algorithm, Euclidean, has given us the GCD. The extended is supposed to also give us the GCD and not just stop there. It will then write the GCD as a linear combination of the two numbers. The two numbers. What I mean by that is that apart from the Euclidean algorithm giving us the GCD of the two numbers A and B, it will also find factors X and Y such that this GCD can be written as a linear combination of A and B. So it will also determine solutions, X and Y, so that X times A plus Y times know that we have a part that finds the GCD. So that part has to be there. So it has to write the GCD first of all. That will now be solving to find X and Y. That is the only part that will be adding. So I've said here, in order to perform computations in modular arithmetic, we have to get familiar with the extended Euclidean algorithm. And we saw how the extended Euclidean algorithm was very important when we were looking at our calculations earlier. So it was almost very important almost everywhere, even finding the inverse and so on. It was very important. Now, the Euclidean algorithm yields a very useful fact that the GCD, in fact, this is supposed to be extended. Extended Euclidean algorithm. That the GCD can be expressed as a linear combination of A and B if they exist, if those two integers exist. For instance, supposing I'm talking of 10 and 4 as my two integers. And of course, I know that the GCD is 2. Can I write 2 in terms of 10 and 4? That's what I'm talking about. That is what the extended Euclidean algorithm then does. After finding the GCD, it can write this GCD in terms of the two numbers. So for instance, you can see what is X and Y, so that 2 can be written in terms of 10 and 4. So when you do that, you'll find that X is 1 and Y is -2, which means that the GCD here, this GCD, can be written in terms of 4 and 10 this way. So this is what this algorithm would then be doing for us. Similarly, if I have these two numbers, whose GCD is 3, can I find X and Y? So that X times this number plus Y times this number gives me 3. Can I do that? Can I do that? And when you do that, you find that X will be -3 and Y will be 14. So that 19 times that plus 42 times that gives us 3. When you use your calculator, you can get 3. Multiply this number by -3, then add this result. You get 3. So this method of obtaining this X and Y and then expressing the GCD in terms of as a linear combination of the two numbers is what we call the extended Euclidean algorithm. Just want to show an example, and then we look at the Rust code that can implement this. But of course, we already know what we expect. We already know, because we wanted the GCD, we already know that that part of obtaining the GCD. And then you already know that there'll be another part of getting those values, X and Y. Now, so I have these two numbers, and I'm asked to express them in this form. Okay, so okay, I have these two numbers, and I'm asked find the GCD of these two numbers, and then express that GCD in this form. Find the GCD of these two numbers, and then express that GCD in this form. That is what the question is telling me. So of course, you can see what we are doing. We are using the Euclidean algorithm to begin with. We are beginning with the Euclidean algorithm. This is the Euclidean algorithm that gives us the GCD. And so we say, how many times does this number go here? Goes there twice, and the remainder will be that. But what about this number into this? So of course, when we are doing our Euclidean algorithm, we call this A and call this B, and this will be our remainder. So our new B becomes this. Our new B becomes this, and our new A becomes this. Our new A becomes that. So 37 then goes here, this number of times, and the remainder is this. This remainder becomes our new B. Our new B. And what was B becomes our A. What was B becomes our A. What was B becomes our A. So B goes here how many times? Once, and the remainder is 6. This becomes our new B when we are dealing with the Euclidean algorithm. And this now becomes our A. What was B becomes our A. Remember the temp. Remember the temp in our explanation above. Temp B. And remember we said that B is then replaced by A, the remainder of A on division by B. This is what it means. The remainder of A on this means B becomes the remainder on division of A by B. And remember, we also say that A becomes the temp. Just reminding you about the Euclidean algorithm. And remember, there was a while loop. The while loop, and the while loop says that this process continues until B is 0. This process continues until B is 0. So this is the Euclidean algorithm. So this process here would give us A as the result, which is our GCD. So look what this, this is our B, and this becomes our A. The remainder is 1. Now this becomes our B, and this becomes our A. What is it here? The remainder is 0. Okay, so our GCD is this. Our GCD is that. Yes, our GCD is that. But now, what is in the temp? What is in the temp here? Our temp before this step, our temp would be 1, is it? Our temp will be 1. And then our B will be what you get. I'm just talking about this step. From this step, this is our B. This is our B. So our B, it's from this step. It is A. Our A is 37. Our A is 37 on division by 31. That's when you get A. Just a minute. I've gone too far. I wanted to explain here how we get the GCD. I wanted to explain how we get the GCD. So from this point, I can see our A is 31. this point, I can see that our B is 1. Our B is 1. So when you go the next step, you begin with the temp to be 1. And then what about B? B is A divided by 1, the remainder is 0. So what about A? A is what was in the temp. So this is our GCD. That's the point I wanted to explain. I wanted to come out clearly at this point, because at this point, what was in the temp, before you begin this step, when you begin at the beginning of this step, what is in the temp is our B, which is that. And our A is that 1. On the next step, our L will be 6. Now, but that is not very important. What is very important is that what is B? Our B in this step is 1, so it becomes the temp for the next step. It becomes the temp for the next step. Then B now becomes A divided by B, the remainder, which is 0. So this is 0. What about A? A now becomes what was in the temp. And our temp, what was there was 1. So that 1 is the GCD. Now, that one is just to explain the Euclidean algorithm that we've looked at already. But this point, we are looking at the extended Euclidean algorithm. So you begin with the Euclidean algorithm, and it has given us the GCD to be 1. And then after that, you reverse these equations. But of course, this program, when you write it, it does not reverse. There's a way it works. And then to the end, and then at the end, without necessarily having to reverse, it will give you the results. Now, so we reverse from here. We make 1 the subject of the formula. So it's the same as that 1 minus 6 multiplied by 5. We had already done this process earlier. We had done this process in our lessons. Maybe for the sake of those who are not there, I can show the working. So since 1 is the GCD, we apply the extended Euclidean algorithm. So that one begins at the point you begin reversing. That is when the extended Euclidean algorithm begins. At the point you begin reversing. But what we've been doing so far up to here is that it's just the Euclidean algorithm. So when you begin reversing, the extended Euclidean algorithm comes in. So you make 1 the subject, the formula, and then substitute. You can see that's what I had done. 1, when you substitute, it's equivalent to that 1 minus that. Now, so this is the remainder here. The next remainder is 6, which is here. You also substitute it. So this is the same as that 1 minus. Instead of this 6, the equivalent of 6 is this. The equivalent of 6 is that 7 minus that 1 multiplied by 1. Then remember this 5. And so on. And what you're seeing, that step that you're seeing is just this. That's the step you're seeing. That 1 minus that 7 minus that 1 multiplied by 1 times 5. Now we open the brackets using this minus and using this 5. Open this bracket. So that 7 times minus 5 would be this. That 7 times minus 5 with that. Then there's this minus and this plus. No, this minus and this minus. Minus times minus is positive, and there's a 5 here. So this is what you get. Then you collect like terms. If you begin with this is what you get. That's 7 negative times 5. But this one is that 1 times 6. That 1 times 6. Now, we had just substituted the next remainder from the bottom. Of course, we are doing it from the bottom going up. So the next remainder is that 1. The next remainder, we are doing it from the bottom going up. And that 1 is equivalent to 364 minus that 7 multiplied by 9. So that is what you substitute where there is that 1. So where there is that 1, you substitute that. That's what you're seeing here. Instead of this that 1, you can see what I've put there. This 6 is still here. Then again, you just open the brackets. Just open the brackets using this plus and 6. Positive 6, just open the bracket. So this times positive 6. Then negative 37 multiplied by 9 times positive 6. So just multiply this 6 by that. You have 54. That 7 remains. Again, collect like terms. This is negative 37, negative 37. And so what is inside the bracket? 5 plus that is 59. That's what you're seeing there. Is 5 plus that is 59. Multiplied by negative 37. And this is here. Now, so the next remainder and so on until you get this equation. Until you get this equation, so that our x is that negative 59 and our y is 124. So our x is negative 59 and our y is 124, meaning that the GCD, which was 1, has been written as a linear combination of the two numbers given to us. The two numbers given to us are 765 and 364. And we were to look for values of x and y, such that this equation is satisfied. Just obtain those. We want to look at the Rust code that implements the Euclidean, the extended Euclidean algorithm. Okay. Yes, here it is. The main function, you have the two numbers. The first number, I call it A. The second number, let it be B, which is that 3 in this case. And then we call the function that will be doing the extended Euclidean, we call the extended Euclidean function with the two numbers. Let the GCD of x and y be this. What the extended Euclidean algorithm will be giving us. And then, so what this means is that, okay, what this means is, of course, these are the results that are supposed to be printed. They were supposed to print the GCD x and y, where x and y are the values we are looking for, x and y. So this is what it prints the GCD of this number, and this number is this, where this number is A and this number is B, and this is the GCD. And then it also prints the coefficients x and y are this and this respectively. So I expect two results. I expect the results. So it's giving us the GCD. Then on top of this, it's also giving us the values X and Y. So this is the main function. Now, this is where the calculations are happening. The calculations are happening at this point. And again, it's a very short code. This function, you input I64, A, which is an I64, and B, which is also an I64. And of course, we've seen in the previous example that you can always change these values depending on the size of the numbers you are handling. And then it's supposed to give us a result that is also I64, I64, then I64, where the first one here is the GCD, and this one will be maybe the X, and this will be the Y. I'll explain what this this first bit means. What it means, of course, what it means is that if, supposing you're given two numbers, A and B, let me say A is 8 and B is 0, and you're asked for the extended Euclidean to find the values X and Y, to find, of course, the GCD of these two numbers, and then write that GCD in terms of the two numbers. In terms of the two numbers, supposing this is what we have. So this is what it's telling us. It's telling us that if B is 0, in this case, like in this case, if B is 0, then the GCD will be A. In this case, our GCD will be 8. If B is 0, the GCD will be A. And then what about X? X will be 1, and Y will be 0. That's what it's telling us here. That if you have been given two numbers where one of the numbers is 0, so for instance, we have 8 and 0, and we want the GCD of these two numbers of 8 and 0. What this is telling us is that this GCD will be 8. It's also telling us, here, I'm just reading this. It's also telling us that X will be 1, and then Y will be 0, so that we have the GCD, which is 8, can be written as 8 multiplied by 1 plus 0 multiplied by 0, which is just 8. So that is what this first bit is telling us. Now it proceeds and tells us that let this GCD and X1 and X2, sorry, this is a case where none of the numbers is 0. This is a case where none of the numbers is 0. What does this tell us? And of course, we know what this part means. We've already talked about it. So you let X be Y1 and let Y be X1 minus A divided by B multiplied by Y1. So this is the bit where we are reversing, This is the bit. So that is how the function then works, how to reverse this bit. And I think, I don't know whether I've included an example just to show you how it will be doing that. Let's just look at understanding the code. Understanding the code, I don't know whether I've included an example. Okay, I began by explaining this bit. It's the only bit we've not explained. The other bit is already known to us. The other bit is just the main function. Then you have this bit. I've already explained this part. So the part that I have not explained is this. and is the one I've included here. Now, so this is what it is. It says the function extended this Euclidean this defines a function that takes two I64 integers and A and B and returns three values which are both I64 integers. So the best case, if B is 0, I've already explained that, the function will return this, where the GCDs end at, and the coefficients are that. I've not included an example. Okay, let's just run the code first of all and see what that runs. That is the extended Euclidean algorithm. Let's just try to run. Now, the thing is, what I'm emphasizing is that we actually supposed to understand what some of these symbols mean so that we avoid a scenario of where we memorize. When you memorize, it might be also hard for you to write a code, any code. You see, for you to write, this is, you see, for you, you actually are in an area where you're supposed to know how to write. So that means, therefore, memorizing may not be a very good thing. So that is why understanding those symbols and what they mean is very important. Now, are you able to see what I've just shared on the screen? From the top. Are you able to see? Lynette, can you see?
Yes, you can see.
Okay, thank you. You can see 1420.
Yeah, we can see.
Okay, thank you. Now this is the code, and you have the first number there, the second number here. We've said that it will give us two results. The first result with the GCD of the two numbers, one, A and B, is this. And then the second result are the values of X and Y are this and this. You can see where I'm pointing. Let's just try to run this. Just try to run and see if it gives us. Yeah, it has told us that the GCD of 1420 and 713 is 1. It has also told us that the coefficients are these numbers. Okay, as usual, let's try to increase this number. Let's try to increase it. Let's try to increase it. Just writing anything, and so long as the number gives us some results. Okay. You can see the beauty here. You can see, of course, a negative here. There's a negative number, and it's taken care of by I. Of course, when you remove this I, the negative number will not come. It'll be impossible. This thing will not be able to run. Okay, let's again increase, just because of time, let's again increase. Just very fast, increase the number. I want it to overflow, and of course, as I showed you, you can change Then change the 64 to another bigger number. Want to see if it will run. Oh, there's an overflow here. What does it say? Consider using type I-128 instead of, you can see, it has told us there's an overflow, and therefore it cannot, this number is bigger than I-64. So for us to do that, we need to change this to a bigger number. It has, of course, directed us. You can even use a different number. There's no problem. 128. Just told us to use a bigger number here because it cannot contain the result coming out of the numbers printed. It cannot contain that. 128. Is there anywhere else? Let's just try to run now and see whether it give us some result. If it doesn't, we can still move it up to a bigger value. Of course, it has given us some result. You can see, of course, the numbers were big. The numbers were big. Look what this coefficient of X and this coefficient of Y. They're bigger than what, you see, when we are talking of I-64, it means we are, it's not the entire 64 range. It's 64 divided by 2. 64, so it's 2 raised to that. It's 64 divided by 2 bits. That's why this number was higher than 32 bits. 32 bits. When you talk of I, so when you talk of this I-128, this is 52 or 54 bit, either side, the negative side and the positive side. Thank you. We stop there. Thank you.
Thank you, Mwalim. So tomorrow we wanted to request Mwalimu we skip tomorrow's session because on Thursday still are not settled, things are not settled. So we have our Thursday session, but instead of physically, we have it online. Maybe next week things will be settled. And then tomorrow we have a guest who wants to teach about zero knowledge circuits and how people can earn money by contributing to open source zero knowledge circuit projects. So tomorrow, 8 p.m., please look out for the poster. It's already been shared, but I'll reshare it tomorrow, time for class. So we can all join and learn zero knowledge and how we can apply the knowledge you're learning here to get projects. So thank you very much, everyone, and have a good evening.